Good morning, everyone. I'm glad to be here presenting my work. The title of my talk is Brain Functional Integration Indicates Brain Effects of TMS. To start, as you might already know, transcranial magnetic stimulation, or in short TMS, is a reliable technique to modulate brain activity and human behavior when it's assessed, and specifically brain activity when it's assessed with fMRI. However, there is a big problem with the consistency of the findings in fMRI. And for example, here in 11 studies that assess the effect of TMS with resting fMRI since 2010, 2/3 of them found a decrease in the functional connectivity, while the other third found the opposite. What is the reason for these heterogeneous results? Well, in general, every study simulates a different region across the entire cortex, and it is known that sensory and high cognitive networks or high cognitive areas has a completely different connectivity profile. We therefore hypothesize that cortical profile of functional connectivity constrains the TMS effects. To test this hypothesis, we stimulate 3 different brain regions in the same subjects, and we assess the effect of TMS by comparing the pre and post-TMS fMRI. For this participant, we select the stimulated region based on the resting state fMRI pre-TMS, so it was functionally targeted. And specifically, we select the frontal spot of the silence network, high cognitive network, the visual cortex as a sensory network, and a control network in a junction between major networks. Importantly, all 3 networks of interest share a similar functional connectivity profile at baseline, meaning that the stimulation of any of them might be able to equally disturb the other networks of interest. To assess the effect of TMS with functional connectivity, we examine 3 different levels, ranging from local signal fluctuations to global interaction between different brain regions. At the local level, we examine the 2 regions the 2 stimulated regions, the occipital target and the frontal target, using 2 local fMRI metrics. The bar plots in the middle the height of the bar plots in the middle illustrate the amplitude of the low frequency fluctuation, while the bar plots in the right give us information about the regional coherence of the fMRI signal or RIHO. So in general, TMS has no local effects for any of the 2 metrics across TMS condition and for any of the 2 stimulated regions that can be observed in the similar height of the bars with the same color that codes the stimulated area. Next, we evaluate the effects of TMS at the network functional connectivity by computing the functional connectivity between the average time series of the stimulated networks and the rest of the brain. In this cortical representation, the yellow areas codes are increase after the stimulation, whereas the blue areas codes are a decrease of that metric. For assistance, the pie charts represent the proportion of networks that were affected in the cortical representation. So, as you might already seen, TMS has an opposite effect on the network functional connectivity, while decrease it after frontal stimulation, increase it after visual stimulation. In addition, as can be observed in the pie charts, there is several high cognitive networks were affected. So, meaning that the TMS effect was not only affecting areas beyond the stimulated area, but also networks beyond the network of interest. That's why we went a step further and we studied the interaction between all these high cognitive networks and the visual network using a graph-based modularity analysis. In short, a modularity analysis finds cluster of regions that are high densely connected, referred to as modules. So in this case, in the metric that we see here, is the functional integration matrix at baseline where red areas codes highly interactive regions. Specifically, we can see three main modules in the diagonal of this matrix, which are also represented in the topological representation. The color codes the network, the visual in red, the saliency in green, and the DMN in blue. And what is also very interesting, like all attention network-related nodes were equally distributed across the networks. It's important to note that the size of the nodes represent the functional integration, meaning that the bigger the node, the more globally integrated. After the stimulation, TMS has, we found consistently the same three modules, which are represented which can be observed in the functional integration matrix and the corresponding topological representation. But what is also very interesting that we have also a consistent effect, a consistent nodal degree effect, meaning that after the stimulation of the occipital node highlighted in red in the top of the slide, which is the topological representation after visual stimulation, and in the bottom, the highlighted node in green after salience stimulation. On the right, we see the bar plots of this nodal degree, which consistently decrease after both stimulation. However, there is an important change here in the functional integration. That is basically what we see in this shape of the topological representation. And we can see that the shape of the visual representation change compared to the salience, which mostly get like the same kind of shape compared with the baseline condition on the left. We therefore try to quantify these changes doing our functional integration analysis. Specifically, we compute the within module functional integration, what is in the y-axis on this scatter plot, and the between module functional integration in the x-axis. Regions that are highly connected within their own modules are represented in the upper left part of the scatter plot, while regions that are globally integrated are in the lower right area of the scatter plots. In addition, the color codes the condition, pre in gray and post in violet. So starting with the occipital on the left, the stimulation of the occipital node, highlighted in the red as well, induce a strong increase in the global integration of the node. And that can be observed when we compare the pre with the post node, target node here, what is like a clear shift from left to right sides of the plot. What is very interesting, like this effect seems to have a spread across all the graph, and that's what we can see when we observe all the violet nodes compared with all the gray nodes. So we stimulate this occipital node, we increase its functional integration, but also this effect was spread across the complete network. In contrast, after salience stimulation, that is on the right, on the other side of the slide, we did not induce any change, either at the local or global scale. Importantly, our control node, what is in the middle, highlighted in cyan, we have this node has an intermediate level of functional integration, and this change was also related with that effect. So it was an intermediate effect on the local integration. So to go a step further, we calculate the distribution of between module functional integration across the complete cortex. So basically, we plot the x-axis on this scatter plot is represented now in the cortical representation in this here. So the highlighted circles highlight basically the stimulated areas, and this suggests that the stimulation of a sensory area could have a similar effect that the one that we observe in the after visual stimulation. That means that when we stimulate a weakly global integrated node, seems to have an spread effect on the complete the global functional integration, while the stimulation of a high cognitive area, similar to the one that we're stimulating the salience network, have no an effect either at the local or global scale. So it might sound counterintuitive that a node that is weakly globally connected drives the largest effect of TMS. But however, it's important to note that this target node, in the case of the sensory, is highly connected within the nodes. That means that this visual node was mostly interacting with the nodes within the visual network. And so it seems that the stimulation of a highly locally connected node that is the global effect of TMS. And this is observed, that can be illustrated in this bar plot that visualize the ratio of functional connectivity within and between the networks. So in summary, or to conclude, TMS has rather distant than local effects, but global spreading of TMS depend on local functional integration. Therefore, we suggest that the brain functional integration is a predictive marker for the spreading effects of TMS. So I want to thank my supervisor for all his help and support, my collaborators who helped me with the acquisition of the data, and to all of you for your attention. Thank you very much.